Thanks everybody for coming. Yeah, I'm going to talk about this thing called structure generation, and why. Like, I think it's potentially next big thing in the AI world. It's kind of big, but it's not as big as it potentially can be, right? And yeah, the outline is I'll just quickly go through the why researchers are important in deep learning and in the modern AI boom. What's the structure generation? Then what APIs are provided by, say, OpenAI or Anthropic, and the future outlook. I also have a notebook that can demo some of the ideas, but well, you'll see, right? So let me give you a little bit of history that you know that the open, like this ChatGPT OpenAI thingy boom happened 2 3 years ago, right? And before that, the big thing was not really the chatbots and LLMs. It was AlphaZero. It was reinforcement learning. Everybody tried to make reinforcement learning work and use it and kind of apply somewhere. And the biggest achievement in the reinforcement learning world was this machine by DeepMind that plays Go and chess and checkers and other games at superhuman level, and it learns by playing with itself, like play self play, and just achieves superhuman performance from zero without even looking at like humans play it. And the way it works, very simplified. There are a lot of extra details, but there is a deep neural network, and it kind of predicts a next action, next move, given the state of the game, right? The state of the game that as it sees it. So this is called a policy, right? So you have an action given the state, and the theta are the parameters of your model. These are weights of the neural network, etc. And you can optimize it so the network tries to learn something from this. And there's another part of the system, and this is abbreviated as MCTS. MCTS is Monte Carlo tree search. Right? So what actually happens is, as the system plays these games, it builds a tree and build a tree of different states of the, in this case, of the chessboard, right? And given each of the moves, you can move down the tree of potential states. And the resulting state back propagates to the root node, and you can evaluate. So you see what the potential future states there, evaluate them, and then back propagate this information to the root node and train your network. So you make a move, then you repeat the process, and you train your network on the result. Like when you lose, you can propagate the reward up to the each of the states, right? So intuitively, what happens is MCTS executes the moves and builds a search tree, and then there is the feedback loop from MCTS, from the symbolic system to the neural system. And this feedback loop is something that I would already call neurosymbolic. Neurosymbolic is like all the hit now. People think about, oh, we have a neural network and a symbolic system. Let's make them kind of interact. But I think that it already kind of happened, and people already have something that is neurosymbolic. And it's not only that this algorithm is kind of trains the network, but it also works in an opposite way. The neural networks kind of learns about what is the search algorithm, right? And it kind of learns how to efficiently use the search algorithm to better explore the potential future moves, right? So similar to how human thinks about like pattern matching and then calculating moves ahead. So that's how AlphaZero works. What about the LLMs and how is this relevant to the things? So LLMs operate on tokens, right? The way typical LLM works is that you have a string, you can have a collection of symbols, and there's always a thing called a tokenizer, right? So it grabs your plain English text, and breaks into little chunks, right? And each chunk has just an integer number associated with it. And so each of these smallish chunks is a token. Then they pass through your neural network. And each token out of the whole dictionary of tokens receives a probability like of its either being a next token, or in this case, it's a BERT network. So it kind of tells you for the masked thing, it predicts a separate token, but it's not that important. The point is that there's these tokenizers are an integral part of the LLMs, and you can kind of add special tokens for special features. To look at how the tokenizer works on your text, you can go to this OpenAI playground, this one, right? So if you go to the tokenizer site, and you type something like Imandra, right? Right. So you see that it breaks it into two pieces. So there's im and andra, because it doesn't know the word Imandra. It's not in the dictionary. So it breaks it into two tokens. So 1707 is a token for im, and 25713 is a special token that attached to the previous token. And it's the Andra one. This one is im, and this one is im, but 45519 is the Andra standalone token, and 25713 is the one that attaches to the previous token. So tokenizers are weird in this sense. There's also a lot of issues with the fact that you can tokenize the same string in a different way. You can have like a single letter tokens, and they also collapse to a word that's kind of could be represented as a single token. Typical tokens like Paris, right? So if you take Paris, right, so you'll have just a single token associated to a common word in the dictionary. So that's about tokenization. How does the LLM then works? Well, it also performs, so all the typical LLMs that we have performs its research, right? So the ChatGPT one, Llama, Claude, etc. What they do is they predict the next token given the context of the previous token. This context is typically called prompt, right? Or prompt is something that you start with, and then it appends tokens in something that's called autoregressive process, right? So you predict the next token, and next token, and next token. The issue with this is like simplified in these classic examples. So if you start with the token the, and then you go dog, and you do and you go greedily, right? So the most likely token that your LLM predicts is the nice, and then woman. So you go the nice woman, but actually the most likely path through the tree is the dog has, right? So if you multiply 0.5 by 0.4, you have 20%, and if you go the dog has, you'll get how many? 30. Well, you know what I'm saying, right? So this ray through the tree is more likely that that ray through the tree. And what LLMs try to do is they try to find the most likely path through the tree of potential tokens. But the size of the dictionary, the list of the tokens, is about 40,000 or even more. And you cannot just completely explore the tree to find the most likely one. So you do some pruning, and the process is still necessarily stochastic. You choose a random, you choose a couple of most likely subsequent tokens, and you keep exploring the tree, doing the Monte Carlo kind of search, right? There's the number of algorithms that do this. When you go to OpenAI Playground, or when you use the API, you have these parameters, right? You have the temperature. Temperature is the most well-known parameter, right? It tells you like how stochastic you have to be, or if temperature is equal to 0, you do the greedy search. As soon as you increase the temperature, you have a chance of selecting a lower probability token and explores the tree better. Right. Top P is exactly like how do you prune the tree at the exploration. You really don't want to take low probability tokens anyway and cut off the low probabilities. There are other parameters. You can add some penalties on repeatedness, or on uh, uh, repeating, etc. There are other sampling algorithms. There is like top k, top n parameters that also kind of stop the exploration, and you can play with these generation parameters for a while and to get your best result. And that's something that in our context, when you use an agent, if you want an agent to be like more verbose, you can you can increase the temperature, and it's kind of more creative and better at generating stuff. So this is call back to the MCTS things that I've been describing at the first slide, right? So we virtually doing the same thing. There is a neural network, and there is a sampler, and we generate stuff. And again, there is a feedback loop actually. So the way we can train these network and post-train them and improve these networks with reinforcement learning with human feedback. Is essentially the neural networks learns about the fact that there is a sampling algorithm, and it should explore this sampling algorithm better and find the better solution through this sampling. So when these neural networks are instruction tuned or like tuned with feedback, they also kind of implicitly know about the sampling algorithm, and it's already kind of neurosymbolic. So the next point is, what is the structure generation or like guided sampling? There is a little bit of confusion about terminology. I call the whole thing structure generation, but different authors and different places call different things structure generation. In most general idea of structure generation is that when you do this tree search, you just constrain what's your next sample token. In the simplest example would be, so you have a start of the sentence, right? And you want to have only valid arithmetic expressions with 3 tokens in them, right? So just you're allowed to use only 3 tokens. You run as variable x, a number 2, or plus sign, right? So at the beginning, you cannot go with a plus sign, so you forbid this token to be generated. So you get either x or 2. If you generated x or 2, then you are allowed to generate plus, and after plus, you can only generate a number, right? So this is very simple, like straightforward grammar-driven generation. But you can generalize this idea to whatever grammar or even whatever algorithm for exploring this tree you can have. So I have a little Colab notebook for this. The issue is that the models that you can use on Colab are kind of tiny and they're a little bit stupid. So the best one I found is this tiny llama. I will not rerun it because it takes a little bit of time to load in the memory. But yeah, you just do you import your transformers and you load the llama from Hugging Face. It takes a bit of time, and you can use it locally here on the Colab in your notebook. So if you write this typical chat template, so you have a system message, and you say that it's like, yeah, your friendly chatbot, and then you ask it what is the advantages of formal verification, right? I just did that, and it converts it to like a template that is just plain text, and this is special tokens that the model knows about, learned how to use. And I fed it to the model, asked it to generate it. So it's a standard generation function in Hugging Face, and use some default parameters, and that's what the model returned to me. It's actually pretty good. It kind of says highly accurate method checker correctness software system. So like even on Google Colab with a small amount of RAM, you have a working model that generates reasonably good text. And what I can do with this is the next thing is the following thing. So I constrain the generation to only 3 tokens, right? I have Paris, Berlin, and London as tokens, right? I run them through tokenizer, and the tokens are correspondingly 3681, 5115, 4517, right? So these are my tokens, and I only allow the model to generate those tokens. And I ask it what's the capital of France, right? And I pass it through the model, and it returns me some log probabilities for only those 3 tokens. I'm slicing the output log gets to return me the choice tokens. So only these 3 ones. And it returns that, well, if you pass it already through softmax layers, so softmax exponentiate logarithms and normalizes them. So you get 90% for Paris, 2% for Berlin, and 6.8% for London, right? Yeah, it's sums to 1. Yeah. Yeah.
Thank you.
So yeah, and yeah, you can do what's the capital of Germany output. So it takes, you see, if you run it, it takes 3 seconds. So one of the advantages of this constraint, like single token generation, is it's much faster than waiting for the like hundreds of tokens to generate. So it's pretty fast, even like in the cloud. Yeah, and Germany gives you 99% for Berlin. We can try to, well, we can do UK, right? UK. What about UK? It should be yeah, 99.8. I was like, it's curious what would be if you do USA, right? So like it's not in the list of allowed tokens, isn't it? So it's generally getting confused, right? 30% here, 30%, 30% here. But that's actually pretty cool, isn't it? It's kind of, yeah, all these are kind of equivalent for it, and it doesn't know where to go. So yeah, you can do very interesting like classification and this kind of multi-class classification. People use this approach for many interesting things in that regard. Unfortunately, the model is pretty stupid when it comes to generating code and like formal text. So I tried a couple of experiments with more smarter formal generation, but it doesn't really work that well. Smaller models are not very good at it. But if you can have llama 16 billions, etc., you can actually make Corset generate pretty decent arithmetic expressions or even formal like formally verifiable code, right? So, but yeah, it doesn't. Unfortunately, I couldn't get it working in Colab. So that's the gist of what structure generation gives you. So you just grab this idea, single token generation. You have your logits, and you do research for the whole thing, and you can have your grammar guiding it, or even like more complex algorithms. So what you that's the gist of the general idea of structure generation. But what about the stuff that OpenAI provides or Anthropic provides? So that's the structure generation into JSON. And some of the authors only mean structure generation when it's JSON format or XML format or some other markup language. That's like a structure on top of your generation. But they don't mean that this generic thing that is guided by arbitrary grammar or arbitrary algorithm. So the idea is that OpenAI provides is this thing that you. So first of all, it generates only valid JSONs, and second, this JSONs should follow user's JSON schema. So it's even more restricted. The way it works under the hood, at least how OpenAI describes it, they grab the JSON schema, and from this JSON schema, they generate the grammar. So it's under the hood, there is a context-free grammar generated from the schema for JSONs that are only allowed to be generated, right? And in their all self-evaluation, they have this this graph where they say that if you use the strict equal true, so constrained generation, some of the evals get to 100% of evaluation performance. So every single reply in the test set is correct, which is what formal verification people want to achieve, right? So that's the performance that no standard LLM without structure generation can achieve, because you have this temperature, right? So with temperature, you have a chance of selecting a wrong token at some point and go into the wrong direction. But if you constrain it, you're completely constrained to generate only valid formats, valid JSONs, and valid syntax trees, right? So another thing that the OpenAI provides is a couple of supports for the SDK code, right? So on the left, I have an example that they provide for Python. In Python, you just write your classes using pedantic, right, Bayes model, and you have like an enumeration type here. So this is the code for database queries, right? So the queries query some table, you ask for a list of columns. There's a bunch of conditions that you can apply, and you do order by, right? So the condition is select a column, which operator it is, and you can, as you say, like there's some parameter, some value, string, integer, or value from another column, right? So it's pretty standard thing. And in Python, you write this pydantic model, and then this pydantic model automatically generates for you JSON schema for JSONs corresponding to this. And then under the hood, pydantic deserialize it from the JSON into those classes, right? Same thing they implemented in JavaScript. Like this is one-to-one corresponders ordered by the enum. Dynamic value is like an object, etc. So JavaScript has as well SDK support. What about a camel? Do we have this in a camel? So I kind of self-promotion. I have this generators library that I've been working on for a couple of months. And in the generators, you write camel types. So you have this variant type, the record type here and there. Forgot a curly bracket here. This is the variant with parameterized variant, right? So string number of dynamic value. Query, these are the list, etc. And if you then want to use OpenAI, for example, and has the same thing, schema generation plus JSON deserializer, you write the code similar to decoders library, right? So there's the monadic code with monadic bind, where you say which fields you want, or which enum entries you want, or you have the any of, similar to the decoders library. And then this generator automatically generates a schema for OpenAI to eat, and the corresponding JSON deserializer as a decoder to decode these JSON types. So we have this support in a camel, which could be pretty useful in those applications. So that's the thing about the whole stuff. But there's like why I think it's important, and we kind of have to focus, especially if we're in the business of formal verification and formal reasoning about stuff that LLMs generate, right? Because this is an interesting paper called "Let Me Speak Freely," and it complains about the OpenAI JSON-based generation, and they try to use JSONs in open models, and they show that performance degrades. So it's like the JSON generation degrading performance of the models. I think that like they made some ideas about this, but I think the fundamental reason why JSON generation is degrading the performance is just because JSON needs so many tokens. It's too wordy, right? So if you want to, you have an arithmetic expression 2 + 2, then you just need 3 tokens to represent it as an actual string. But if you have if you represent the same as a syntax tree for this, so it's like a binary operation, add with left-hand side number 2. So you have order of magnitude at least number of tokens, and that's the main drawback why using JSON is when you try to use structured generation, your performance getting sometimes you're losing performance if you compare this to generation of just an actual code. I think that's the fundamental reason why it's not so well working. So if it's eating so many tokens, why don't we just generate it guided by the grammars, right? Why OpenAI doesn't provide grammar guided generation? Because it exists in open source community. So there's a constraining by eBNF and llama.cpp project. So you just write your grammar in your BNF notation, supply it to Llama CPP, and it works out of the box. You can generate very complex expression guided by grammar. There is another thing called guidance, and it's by Microsoft. Microsoft supported. It's more of a template based, but you can really write also the template based guided generation with this language, and it's also, if you have access to raw weights of the model, it can kind of work as a grammar based generation. Guidance also support OpenAI, so you can connect it to OpenAI. But when you try to do some like grammar weight based things, it complains that OpenAI does not let us access logits, so we cannot do this part of the functionality of our language. And the reason I think it doesn't work is because if you have if you can supply, for example, OpenAI with grammar and ask it to generate something, you can reverse engineer the model, right? So you can have access to logits of the model, and as a result, like, it leaks the information about the model, and they don't want it. And so to protect the privacy of the model weights, they don't let you do such a powerful thing. And the thing is, there's more and more news that Microsoft, that Mistral, and that Google Gemini, they are planning to just give you on-prem models, so allow you get the weights of the model and run it on-prem. And as soon as you can run it on your hardware, you have a control of what it generates, and you have access to the output logits. You can start using these powerful techniques and generate things with grammar and guided generation. But why stop at grammars? That's another question that I'm asking myself. So, like, you generate the code, and I've been trying to generate, for example, Prolog code, right? With structured generation. And one of the issues that in Prolog or in any other language, you first define your types or your variables, and then you want to reuse this. So you can have like wrong variable name, just unknown variable, or you have a type check, type error, right? And you know that your variable is an integer, so you cannot like use it as a string, right? But why can't you restrain your generation by type checking information or variable declaration information? You can do this as well, right? Why not execute the code, right? So if you have every code and it's generated, you can just try executing it, see what's happening. And if it fails, you backtrack and try to generate down your sampling tree. And finally, why don't you just formally verify at some point? If you at some point that this code looks good and you can try to verify that it makes sense and backtrack on failures, you can even do this, right? So that's the main idea, that I feel like it could be a big thing, and it's very very promising to look at those structured generations, guided generation things. And that's my last slide. So thanks you for your attention. And I hope you have any questions or
Great
comments.
talk.